Alright, we're going to need to start working on sets in a little more detail. And to do that, we're going to use a visual tool. And the visual tool we're going to use is a Venn diagram. And so in a Venn diagram, we have some representation of what we're going to call the universe. I'm going to just label this with a U. And the universe contains all of the elements that we might need. And then what we can do is inside of the universe, we can contain elements in another shape, usually a circle, sometimes it's a rectangle, but it could be any shape, any geometry, and sometimes making it look smushy or look odd can let us know that the boundary is not well defined, right? But some visual representation of things inside of it, and that's going to be set A. And so we have the universe, which has all possible elements, and then we section off and talk about some elements that are unique to a set themselves. Well, drawing the circle actually creates two spaces. There's everything inside the circle, and there's everything outside of the circle. So let's see here if I get my tools to work for me in the way that's fun and neat. So I will color in set A, and I will color in everything that isn't set A. That's a little bright. No, that's bright. That's like the 1980s came back again. Let me tone that down a bit. I'll tone down both of these a bit. Let's go for a slightly more muted tone. That's not so 1980. Girls just want to have fun. Okay, anyway, that's still bright. And so we have our universe, set A, which is in the blue, but the orange is something that isn't set A. And what I'm going to do here is I'm going to label that which isn't set A as A's complement. And we give the complement a little prime mark. And so I can talk about everything in the blue, or I can talk about everything in the orange. But notice by defining A, I create this outside space. In fact, if in the reading in chapter 1, this is kind of like the two faces that make the goblet. We have the positive space, the positive definition of A, and then we have everything that isn't A. And this is going to be a useful way for us to talk about sets. And the things that we're making here are called Venn diagrams. And the purpose of Venn diagrams is to help us visualize things we can do with sets. So let me make a set and give it some elements, and I won't try to be so bright on the colors there. Let's see here. And so here's my universe. So here's my universe, and I'm going to put some elements inside of my set. So I'm going to put inside of my set, I'm going to put a W, a triangle, a $sign, the letter M, and the number 5. And so that's my universe. And what I'm going to do then is I can write this in my roster notation. I'm going to say that my universe is the set of W, triangle, dollar, M, and 5. I'm going to come out here. I'm going to make a set. And that's going to be my set A. And so I can come down here, and in my roster notation I can say A consists of the elements W and triangle. And then I could say the complement of A, or the things in the universe that are not bounded by A, is dollar, M, and 5. And so this is what a Venn diagram does. It's a way to talk about and visualize sets, and to kind of think about the idea of what binds sets. What is the boundaries between these objects. And in the end, we're looking for patterns. And sometimes the boundary patterns are easy to describe. Other times, what's not in the set are easy to describe. But this gives us a visual space where we can start playing with it. And we can start using the ideas to build upon each other. Right, I'm going to keep drawing some Venn diagrams here. Probably going to make sure I keep having paper. I think I'll get one more here. Alright, inside of this universe, I'll draw two different sets. And I'm going to call these, this will be set A, and this will be set B. And these two sets we're going to say are disjoint, because there's no elements that are in each other. They don't overlap. And so there's nothing in A that's in B, and there's nothing in B that's in A. There's no sharing of elements. And we see this visually because their boundaries are such that nothing inside of A is inside of B. So that's what a disjoint set would look like in a Venn diagram. Let's come back. I'm going to clear because I ran out of paper. Go back up. We'll keep adding to our definitions here visually. So let's make another. So here's my universe. And in my universe, I'm going to make a set A. Or set B, I'm sorry, and a set A. So I'll make two sets like this. So I'm going to come back here, and this is A, and this is B. Now notice, all of the elements in A are within B. A is completely contained within B. Notice how my visualization and my words are matching how we described sets before. And I can say A is a proper subset of B. Let's visualize some more sets here. Get a universe. Come out and I'll draw a set A. Come back in and I'll draw a set B. And now I can say this is set A, and it's also the boundary for set B. I have two circles here, and they're exactly the same circle. And so I can say set A is equal to set B, and A is a subset of B, and B is a subset of A. And so this is what equal sets would look like. And I think the common Venn diagram that people see, you see them on memes all the time, is you have one set of elements. You have two sets here. This is set A, and this is set B. And we have this overlap. We have some shared elements. And for emphasis, I'll color that in, is that there's some set of elements that are shared between A and B. And those are common regions between the two sets. Right. Not out of paper yet. I've got room for this last one. So let me get some elements onto here. And so I'm going to make A through G. A, B, C, D, E, F, G. And so I have a universe, and it is A, B, C, D, E, F, and G. And I'm going to come over here. Let's see if I can, oops, wrong. I messed up. There we go. And we'll make set A. And so I'll come down here and define set A. Set A is the elements A, B, C, and D. And I'll also come over here and I'll make a set B. That's not how I want B. Let me make B. Nope. So the hard part about drawing programs sometimes is how we do curves. Alright, and we'll make that set B. And so now I can talk about set B as the elements D and E. And if I look, I can say the elements that are in A and B is D. And I can talk about the elements in A but not B. So the elements in A but not B. And that's going to be ABC. Right? I'm in A but not B. So not the shared things. And so we have this way of using these visual spaces to talk about elements. And what we're going to do is we're going to end up using that word that I used before, the complement, to talk about these things. All right, let's clear my sets out of here. And so go back to our basic set. And we can kind of talk about a complement. Right? We talked about it in the beginning, but let's define it using set builder notation. So let me draw A here. So this is my universe. This is set A. I think I will put my letter inside of it right now. And this is A complement. I might sneeze. I apologize if I do. And so I can say A's complement is the set of all elements where X is in the universe and not in A. I have to put the not. And so everything out here is in the universe, but not A. And so notice what we're starting to do here, right? Well, we drew some weird pictures. What math are we doing with them? What are we trying to do? Well, what I'm doing is I'm taking our symbols, our set builder notation, and I'm having it relate back to pictures. And that way we have a mental image of how these things contain and talk about grouping objects. And we're slowly going to build our way into actually putting specific objects into there. And then looking for where they overlap, don't overlap, and what we can do with them. Alright, so one of the things we want to talk about then will be the intersection. And so we will create a new notation to talk about intersections. And so I could say A intersection B. Well, that's all. I also, in my mind, think of this as A and B. And what an intersection is it's the way of talking about the shared space. So if that's A and B, this bit here is, let me write it in a different color, A intersection B. So A intersects over B. It overlaps. It's the overlapping space. And that green showed up really well, didn't it? There we go. We'll make it bolder and brighter. A intersection B. And so it's the overlap of the two. And so what we can say is A intersection B is equal to all elements X such that X exists with, or is an element of A, and X is an element of B. And that's why I tend to say and when this is here. To me, this definition reads right into these words when I'm thinking about it. And it's the stuff that they both have. It's all the shared bits going to the intersection. Well, let's look at a set intersection with actual numbers and not a drawing. So I'm going to take a set of, I won't use variables for it, I'll just use 7, 8, 9, 10, and 11 will be the first set I'm looking at. And I'm going to look for the intersection of it with 6, 8, 10, and 12. And so I need the things that are in both. Well, this is a straight series of numbers, 1, 2, 3, right? It goes by ones, 7, 8, 9, 10, 11. And this is even numbers. So 6 isn't in here, but 8 and 10 are. So 8 is in there, and 10 is in there. Right? 8 and 10, but 12 isn't in there. And so we can say the intersection between these two sets is the set of 8 and 10. And so we grab the common elements out, and they become usable for us for other things. Well, if we have intersections, we can also have unions. So A union B, and the union of the set is such that it really talks about grabbing all of the elements. And so I could write this as all elements, it's the set of all elements X such that X is an element of B, or A, or X is an element of B. And so I see this as an or. If you ever program computers, do computer logic, ands and ors have a similar notation and a similar feature. And the word or pops in here. But with A union B. And instead of drawing this, I think it'll be more inclusive. I'm going to use the same numbers. So I'm going to use 7, 8, 9, 10, and 11. And I'm going to do the union of that with 6, 8, 10, and 12. And so now I need an or. I need to collect everything. And so, well, I have 7, I have 8, I have 9, I have 10, I have 11, and I have 12. Right? Because that's there, I grab everything. And one of these elements is either in here or it's in here. And so I pulled it from either of these. And so that's what my or my union does for me. Well, the empty set is kind of neat here, because the empty set kind of hides behind things in the background. And so if I can go A and the null set, well, the null set's empty, so there's nothing shared, and so this creates a null set. And A or the null set, well, the null set is empty, so I get empty plus everything in A. And so this is how our null set works with our idea of intersection and union. And this lets us do something that we're going to call performing set operations, because what we're doing now is we're doing things where we take one set and we manipulate it to get a new set. And in mathematics, that's called an operation. When I take one thing, I do something with another thing, and it creates something new. Now, we're used to that with like operators as being addition or subtraction or multiplication, but here we're going to do set operations. So let me clear my sets here. Oops. I'm going to go to a blue backing. And so what we always do is set notation specifies the order in which we perform these operations. We always start inside of parentheses and work our way out. Let me get a universe here for you. So I'm going to have a universe of the numbers, natural numbers from 1 to 10, inclusive. And what am I going to put in set A? I'm going to put in 1, 3, 7, and 9. And B is going to be 3, 7, 8, and 10. And so, that's the first thing I'll do, is find the union of A union B. And so A union B is everything that's in both. All of what's in both. Let me get my words right. 1, 3, 7, 8, 9, and 10. Well, I can take A union B, and I can take its complement. Now, a way of looking at this is I can look at my universe, and I want things that aren't in either of these. So if I go through my list, hey, I've got 1, so that's not in the complement, but I don't have 2. 3 I have, but I don't have 4. Or 5. Or 6. But 7, 8, 9, 10 I do have. And so that should be the complement, 2, 4, 5, and 6. And so these are the things that are in both A and B. These are the things that are not in either A or B. I think I'm going to use either or. These are the things that are in either A or B. And these are the things that are not in either A or B. Not. And we have what's in both, what's not in either. Alright, let's look at removing parentheses. Make sure I get the same right universe. 1, 3, 7, 9, 3, 7, 10. Yep, it's the same universe. So I'm going to look at the complement of A and the complement of B. So I think the first thing I'm going to do is I'm going to do this in parts. I'm going to find the complement of A, the things that aren't in A in my universe. So the things that aren't in A is 2, 4, 5. Right, because they're not in there. 6, 8, and 10. It's not in A. I'm going to end that with the things that aren't in B, which are 1, 2, 4, 5, 6, 9. And so when I AND these, let's see, they both have 2, they both have 4, they both have 5, and they both have 6. Well, we can also do this with a Venn diagram. So we can make a collection of numbers in a Venn diagram in a universe. Let me get my universe drawn here. Let's see. I'm going to use the Roman numerals 1, 2, 3. I'm going to use pi square root of 2 e to the I pi, which is -1, right? E square root of -1, which is I, 10 to the 100, 2 to the Aleph 0, and Roman numeral 4, and 777. And so here I have a universe. I've filled a universe, put universal things. And I'm going to come over and I'm going to make A contain these things. I'm going to make B contain these things. A and B. And so I can look at A union B. I'm going to put my set down below here. And so that's going to be everything that's in either or. So I get all of these things. Everything that's within here is within my set. Someday I'll learn to draw Aleph properly. And that's my set of the union of the two things. Well, I could do what's not in the union of the two things. And so these are the union of the two things. The things that aren't in it are the Roman numeral 4 and 777. I can look for A and B, which are the things that are shared. Roman numeral 2, square root of 2, and square root of -1. And so the Venn diagram helps us organize things instead of going through the list. So I can look at what's not in these two bits. Well, it's the things that aren't within this region. 1 pi e 3 e to the I pi 10 to the 100 2 Aleph 0 IV and 777. And so the Venn diagram breaks things into regions, and I think your textbook was using these to number that there are distinct bounded regions. And I was going to come over and I was going to use color to do that, because I like color over numbers, especially when talking for numbers. And so there's a distinct outer green region. That has a distinct orange region. Right? And there's definite areas that are different because the boundaries of these Venn diagrams distinctly collect things in different regions. And then we can access those different regions by grouping things together. And that's what our set operators do. They let us group regions in our space together. And I focused on the words that we would use. And so the one thing we have to look at here is how cardinal numbers come into play with our sets. And so if I have the cardinal number of a union of two sets, then what I'm going to get is I'm going to get all of the elements in A plus all of the elements in B. But if they share anything, I have to get rid of the things that they share. Otherwise, I'm double counting. And I'll show you what I mean by that. So if I want the cardinality in here, I'm just going to put dots in for my elements. 1, 2, 3, 4. And so, a couple more here. If this is A and this is B, the cardinal number, the cardinality I have for this is 1, 2, 3, 4, 5, 6. So NA is equal to 6. There's 6 things in A. But the cardinal number of B is 1, 2, 3, 4, 5, 6, 7, 8, 9. And so if I'm looking for the union of these, it's everything they have together. Well, notice if I count everything in A and I count everything in B, I've counted these things twice. And I can't do that. And so to get the total number of things in here, let me just go right into the formula. NA is 6 plus 9 minus, well, what do they share? So N of A and B is 2. So I'm going to subtract 2 from this. So it's 13 minus 2, or 11. Well, let's count everything. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Did I just... Oh, I did 7 instead of 9. Bad Jeff. Bad Jeff. Get all my little dots out of here. All right, this is called bad handwriting, Jeff. Sorry about that. That's a 9, not a 7. So 6 plus 9 minus 2. That's 15 minus 2 is 13. Now let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And so what happens is when we share things, we double count them. And so we have to remove that double counting with this. Now, what's really, really neat is if there was no sharing, if A and B were separate, this would be 0, and I would get the total of the two things coming across. So set operations really help keep track of things that are needed for us. All right, that's section 3 here. Practice the homework. Email me if you have any questions.